everybody. Today is going to be all about going from where you are now, which is you are making predictions and you can compute some numbers, to sort of interpreting those numbers and using them to draw conclusions about what works, what doesn't work, and if A is better than B. So there'll be a bunch of different versions of that we're going to talk about today. Like last time, I'm going to have you keep a running example that is tied to your project. If you wouldn't mind, please write down just a brief summary of like what is your baseline approach to your problem, and then list a couple ideas for things you're going to try out. If the baseline approach worked, what would you do next? Anyone who's finished want to share what they wrote? How about Casey?
One thing I was going to do is change the class weights, like play around with those.
Doing some kind of a balanced classification, and then you're going to change the weighting on the different.
Exactly. Yeah. Try to make it a little bit more extreme to see if that helps.
Tiziana, what about you?
I have no clue because I'm still trying to understand how to get the output out of my model.
So fine.
Sorry.
Cool. Thank you.
Sure, and sure. So my baseline is just to throw stuff at a resonant 50 and see what happens. And then from there, like similar to the case, I have a lot of class imbalance. So I want to try weighting the classes, and then probably a harder one is to try something that's pre-trained on the audio set instead of.
So today we're just talking about how do we demonstrate progress, and we're going to, this is the mental model, right? You have some baseline you start with. You try something and it's worse than the baseline. That is what we call not progress. You try something else and it's better than the baseline, and you're happy, and that's progress. But it's not quite this simple because the kinds of comparisons you're making here matter. The conclusions you draw from data like this matters. So you could try something and try something else and have numbers that show that one of them is better than the other. And it can be inaccurate to say that that's the right conclusion. We're going to get into that. So the title lecture is Fair Comparisons and Ablation Studies. So a fair comparison is one that provides evidence that method A is better than method B for some task. So we're going to get into that a bit more. Tricky to define what fairness is. And an ablation study is a set of fair comparisons which show the benefit of each component of a method. Computer vision systems often have a bunch of different things you stick together, right? You've got a bunch of terms in your loss function, you've got pre-processing steps, all that kind of stuff. And once you put them all together, you can get some performance numbers, but you don't necessarily know which things are most important for getting you where you are. We'll start by talking about fair comparisons. This is just the operation that I mentioned before. Fair comparison provides evidence that method A is better than method B for some task. And so this is a simplified computer vision pipeline where we have 3 stages. We have pre-processing. So these are things like how do you crop your images into your augmentations or whatever. We have the architecture, choice of model, and then we've got the loss function. So for instance, for pre-processing, maybe method A is using random horizontal flipping for augmentation, and method B is using no augmentation. Or for architecture, method A would be using a ResNet 50, method B would be using a VGD16. And for loss functions, maybe method A is using focal loss, and method B is using cross-entropy loss. So these are just to give you a flavor of the kinds of design choices we're talking about. And so you're not really ready to answer this yet, but I think it's fun to like sit down and try, because I had a really hard time actually coming up with a good definition here. So give it a whirl. What do you think makes a comparison fair, and what makes a comparison unfair? I've got got my attempts on the next slides. Anyone want to give it a shot? Anna?
My take is that a fair comparison would be, you only change one thing. So you're not gonna like, if you're comparing a resident 50 and they're 16, you're not going to like give one more data than the other or something to train on.
Yeah, I think that's a good one. Anyone else have one?
I was thinking more about like the final comparison, and I wrote a fair comparison should be comparing performance across all three of those categories and balancing the trade-offs inherent in each of those.
So in that case, do you mean something like, so there's pros and cons to each of those choices, like some of them are
Right.
simple or complicated or things like that, and you want to weight that, like with those, like usability factors and things like that into the comparison?
Yes.
I'll show you my guesses. My version 1 here was basically what Anna said. The comparison is fair if there's really only one reasonable explanation why method A is better than method B. So you did a comparison, you ran some numbers, one number is higher than the other, and because you changed only one thing, you have a good candidate for what explains that. And so an unfair comparison would be one in which you can easily think of several reasons why method A might be better than method B in your experiment. Or you see the numbers, you're like, well, okay, but I changed the architecture, I changed the loss as well, and so it's not clear that the preprocessing is what's responsible for the change. The thing that I thought about this is like, well, okay, but like, what if we're comparing fundamentally different methods? Like if you have a CNN and a random forest, you can apply both to the same problem, but like there will always be differences between these, and you can never boil it down to just one difference at a time. Does anyone have an idea for a notion of fairness that can like deal with this fact?
For the method to have the same inputs and then to compare the accuracy or the error of the outputs or the predictions.
Yeah, I think it's definitely right. You gotta definitely use the same inputs and compare the same outputs in the same metric. You can't get anywhere until you made all those things for sure.
I think a lot of, at least in that example, comparing a CNN versus random forest, it comes down to like how you're actually evaluating the goodness of either of those. Does that make sense?
What do you mean?
So like just making sure that you're like evaluating on the same metrics, even if the task might be like slightly differently formulated for either model. I'm not sure if that makes sense. It makes sense in my head.
So what I think is like, yeah, we're definitely talking about the same task with the same and same metrics and everything.
Yeah.
We've got different models. So there's some things where you can choose whether to use a neural network or a random forest on the same input data for the same task. So the thing I was thinking about was, you know, another operational definition of fairness is that you see the method A is better than method B, and you can't really think of any way to help method B do better. Right, so this is like your, you know, method B might be your random forest, and if it underperforms the CNN, it's not because you did a bad job building the random forest, it's because, you know, you've done everything you can, and this is as good as you can make it. And so an unfair comparison would be if you run these numbers, and someone who's good at random forest comes along and is like, oh, there's a lot of ways you could just do that better. You know, you haven't given the random forest everything you can to allow it to do well. So no perfect answers here, but these are two operational definitions of fairness that I think are good to keep in mind.
It's also really hard to do this right, because often the things you're comparing against are things that you're not an expert in necessarily. So.
Like the random forest is a good example. Like I don't do those all day long, so I'm not as good at tuning them as I am at tuning CNN sort of stuff.
Yep.
Well, so one, just to step through an example really quickly, suppose we're interested in comparing two loss functions for, we've got a resnet 50, or whatever, and we want to compare two loss functions to see which one's better for our task. And so, do we want to use the same pre-processing? So this is the same augmentation, same image sizes and all that. And I think, yes, we do. We want to make sure the pre-processing is the same because it has nothing to do with the loss function. Do we want to use the same architecture? I think, yes, we do. If you have a resnet 50 and you compare it against a VGG, that's going to be an obvious source of difference between the two methods. Do we want to use the same hyperparameter values?
Learning rate might be very different for different loss functions.
Does anyone want to have input on that?
I think that probably goes back to your version 2 where, if one type of loss function just needs a different learning rate to function, then you could point to, like, if you just compare them with the same learning rate, someone else could say like, well, this would actually be a lot better if you change learning rate in this way for that type of loss function. So I think in that case, trying your best in each case to make it a fit with the loss function you're using.
Yeah, that's the content of this question. Is that, yeah, you don't want to blindly make everything exactly the same. Because different methods might need slightly different, like hyperparameters, for instance. So what you do want to make the same is the amount of effort you put into tuning the parameters for each method. So if you spend, 100 GPU hours tuning the learning rate for the method you like better, you should also use the same amount of GPU hours tuning the learning rate for the method you don't like better. And so that's how you make a fair comparison in that case. Does that distinction make good sense? And it's something you should be aware of as you read papers, right? Is the people who are writing this paper have a vested interest in presenting the method they're proposing in the best possible light. And so it is very easy to, I think it's very rare that you truly spend just as much effort on your baselines as you spend on the proposed method. And so you should just factor that in as you read the papers. And so in my last lecture, we looked at this plot, and there was a lot of interest in it, so I thought we would revisit it in this context. But introduce it one bit at a time this time. So this is from a paper from Kevin Musgraves and Serge Boulanger. And on the y-axis, we have performance on some computer vision task. We don't really care what, it's something like accuracy. And each group of bars here represents a different loss function. So that's what these tiny text labels on the x-axis are different papers. They propose their own different loss functions for this task. And then each color within a group of bars is a different data set. So they evaluate these loss functions across 3 data sets, kind of standard computer vision practice to use multiple data sets or stuff like this. So what we see here, if we just look at the numbers the papers report, we see a strong upward trend in the performance over time, which is what you would hope is true when you have a group of people doing research on some topic, working hard on it. And so as you read this, sorry for putting text on the slide. This is the kind of thing this paper is about, is that, like, look, here's a paper that said they do so much better than the previous paper because of their new loss function. And if you dig into the details, it turns out that they use a different backbone architecture as well. And it happens to be one that's much more capable. And so that is not a fair comparison between these two loss functions because you've also changed the backbone architecture, and that's a huge factor to change. And so this is the kind of thing that's responsible for the difference between these two plots. So on the right is what happens when the authors of this new paper use the same backbone architecture, same optimizers, similar amounts of like parameter tuning, all of that stuff to try to compare these loss functions on as even footing as they could. And so this is meant to illustrate that smart people who are trying to do their best at this stuff can easily make these mistakes. And so it's just something to look out for and to be really careful about. And so, earlier you wrote down some of your ideas for improving on your baseline. So think of now an example of like what would be an unfair comparison between one of your ideas for improving on your baseline and your baseline. And so don't everyone pick architecture because we can talk about that one. But, and think about like why would that be unfair? Do you have a?
Sure. So I think an unfair comparison I can think of is having two different sampling rates with audio, because if you have a higher sampling rate, you have higher quality audio. And so if you're feeding one algorithm lower quality, it might have a more difficult time to classify it.
Yeah, that's an awesome example. It's a good one too for a vision audience, because it's the kind of thing we might not think about, that if you're closer to the domain, it'll occur to you that that's an important difference, whereas for a computer vision person, like, to us, it's all images, and so it would be easy for people in our position to not, take that into account. So I'm just going to go through a couple calling this fair comparison checklists, but just a few things to think about whenever you're wondering whether a comparison is fair or setting up a comparison yourself. So we're going to start by saying, okay, you've run some experiment and you find that method A is better than method B in whatever method you're using. Think of any differences that could be controlled for that you didn't control for. So for instance, there's different architectures, different amounts of pre-training, like if you pre-train one on a big data set and the other one on a small data set, things like that. So this is kind of the obvious one, basically like, did you miss anything you could control for that it's clear that now you should go back and control for it? Can you think of any way to improve the performance of method B? So this is back to that sort of second operational definition of fairness, where we want to make sure that our baseline or whatever method is the underdog gets all the help it can get. Because when we're building new stuff, what we want is for our stuff to work, and so we should be aware of that bias and try to make the baselines as strong as possible to counter that. And so similarly, there's a kind of unfairness that's useful, which is, okay, is method A better than method B, even if I give method B unfair advantages, right? If you boost up your baseline by giving it more training data or other advantages, and it's still not as good as your proposed method, then that's even stronger evidence that what you're proposing is a meaningful improvement over the baseline. So it's often nice to think about this and to try it if you can. It just sort of burnishes the strength of your argument that the method A is really doing something good. This is a big one. Have I invested at least as much effort in tuning method B as I have in tuning method A? We talked about this a minute ago, but we have the method that's our favorite and to win the race, and so we tend to spend more time tuning those than the boring baselines that everyone else is using. But it's important to make sure that both methods are getting reasonable amounts of effort for hyperparameter tuning. And then finally, it's really not possible to make fair comparisons all the time. And so the thing you need to do is make sure that you point it out where it still exists in your argument. And so just flagging that is very useful. So a lot of times in computer vision papers, I like to see a limitation section explicitly in the paper. So it's usually towards the end. And it's like, okay, here's the things that are not good about my method. Here's the things that won't work. Here's failure cases. And here's things that are like unfair or not ideal about my experiments. So as a reader, it's very helpful to see that, because then you trust the authors more, which is a good thing. And B, you get a sense for the real utility of the method instead of the salesmanship version of the method.
It's not normal to have limitation sections in computer vision papers. There's a lot of my method, best method papers. Yeah, I feel like limitations is like a standard section. It should be in our.
Yeah. There's different levels of how seriously you're critiquing your method, because there's limitations well, we didn't solve everything. It's like this, ho-hum kind of limitation that is not really a big one. Or you could say things like, there was a flaw in our experiment, so just left out this key factor variation. Someone's really going to need to check that before you take this seriously. That would be it's a more serious critique of your own paper. And so there's levels of that too within this pattern. Okay, so that's fair comparisons. And so I was now going to move on to ablation studies, unless there are any questions about the.
I have a question for you. How much should they care about doing a fair comparison? If their goal is just getting something that will work as well as possible and help save them some time, maybe not solve the problem in fact.
Yeah.
Where, as opposed to trying to justify that a new method is better.
Yeah.
What is the dimension of fair comparison that is most practical?
Yeah, it is a good question. To some extent, the answer is ablation studies, which we're about to get into. But you're right. So this perspective I've been taking is kind of a machine learning paper writing perspective, where it's like, here's my new method. I need to prove that it works better than what's being done already. And so the pair comparisons we've talked about before, maybe if you're talking about comparing against like other people's methods, that's really mostly relevant for like when you're writing your papers. You know, if you need to convince reviewers that you're not wasting your time with a method like a CNN, then you may need to do some version of a pair comparison against a simpler thing that they're used to seeing in their regular reviews. But
No, you can finish it.
I mean, the version of it that's most relevant is what we're going to talk about with ablation studies, which is how you do fair comparisons against yourself, right? You're working on your method and you're trying to figure out what are the chunks of this that are actually useful and what are the chunks of this that are just adding useless complexity.
Yeah, so I guess as a sort of follow-up to that, like what is like the standard for like making comparisons between models for tasks that like I think a lot of people here are working on tasks that like haven't been done before. So like what like is there a heuristic for like making fair comparisons in tasks like that? Where like all of these computer vision papers are like we're running the same models on like the same tasks that we've been doing for the last 30 years. Like what?
Yeah, that's a good question. And so I think it's more about justifying your efforts, right? So
Okay.
Even on the same task, even if it's a brand new task, you still have many choices for ways you could approach it, right?
Mm-hmm.
You could use a random forest or a Resnet 50 or something else entirely. And if you, I mean, maybe to yourself or to your advisor, to reviewers, you need to justify, look, why are you using this big expensive method? You know, I know someone who used something much simpler, you didn't try that, and so you're using all this GPU time and all that kind of stuff. So sometimes you need to justify the methods you're using, especially if they are resource intensive like these ones are. So just as a reminder, Ablation study is a set of fair comparisons which show the benefit of each component of a method. Now that we have the fair comparison kind of idea in the back of our head, we're basically going to apply it repeatedly to little chunks of the method. So the way most methods work, if you have come up with an idea for doing something, typically you start with a baseline and then you add some stuff, right? You add X, you add Y, maybe there are new terms in a loss function or there are extra processing steps or curriculum learning or whatever. You've added something to your vanilla Resnet 50 and now it works better. And so the question is, do you really need both of those things? So you've added two things, you observe a change. How do you know which one is responsible for the change? So this will surprise no one, but the way you do this is that you start with your baseline performance. Then you evaluate the method. If you just add the first component, just add an X, and then we see, okay, great, X is better than the baseline. And then we just add Y, and we see, okay, we take the baseline and just add Y, that's better than the baseline. And then this is the number you started with, which is where you add both X and Y, and you find that, so the bar on the right is what you started with, the bar on the left is what you started with, and you say, okay, this is better than baseline. The bars in the middle tell you that you actually do need both of these things. You need X and Y, both of them help independently, but if you combine them, it's better than having either one alone. So this is kind of the standard structure of what's called an ablation study, where you remove one component at a time and show that each one is carrying its weight.
So in practice, do you do like a grid search over these things, or like what is your approach to? Because there could be so many different things, so many different possibilities.
Yeah, usually you just pick carefully. You don't normally do this with more than a couple of factors, because if you have n things, you have like roughly n squared combinations like this you could do. And so you can't check everything, and so it's typically kind of the highest leverage thing. So if you are proposing a new loss function that has two terms, then it would be very natural to ablate both of those terms without worrying as much about like the architecture or other things that are not really relevant to the method at hand, things that you can hold constant.
So like because I can think of like a very long list of things that would make my baseline better because I haven't exactly spent a lot of time on my baseline yet. Should like the things that will obviously help, like maybe like a little bit of data augmentation or something, should I just include those in my baseline? And then only, my X and my Y can be things that are a little bit more sophisticated? Or like, what do you suggest?
Yeah, that's often the case. So that like the baseline method in most, like in a computer vision paper, is typically like a resonant 50 with some bells and whistles. So it's like, it has data augmentation, it's got some regularization in it. So kind of all of the standard tricks you would use to get one working well on an arbitrary new problem. And so, yeah, nothing says your baseline has to be the absolute simplest thing you can think of. I think for time reasons, we've encouraged that because we don't want you to get something running. But yeah, I think in general, it's a good idea to have your baseline be, kind of include the standard things that are pretty obvious, and then your quote unquote proposed method, and just add the things that you've had to work harder on or that are kind of more interesting or domain specific.
So you remember in Devis's talk this morning when he had that thing that was like, oh, how did we make this, this detection work? And it was kind of like baseline plus loss weighting plus curriculum learning plus, and so like those things, like adding a loss weighting, you'd maybe want to try that with and without the curriculum learning, and then try both of them together and see. But it's interesting because something like curriculum learning is implicitly also adjusting the balance of classes, and class weighting is also addressing balance of classes. And so the two things are like different ways to get at the same thing. What you might actually find is like class weighting helps this much, like here's your baseline, class weighting helps this much, curriculum learning helps this much, them combined is essentially the same. Like sometimes stuff like that is true. And then you can actually then justify it's simpler to implement a loss weight, so that should be like the practice.
Great transition.
Yeah.
And so, one question we could ask here is like, okay, is it worth it to add Y, given that, if you have X, you get most of the way to your final performance. If you add Y, you get a little bit more. And it's kind of question specific, right? You should ask like, okay, if it's 2% is the gain here, is that important for my problem, or is that nothing? And is Y like super cost to me? So something like, like curriculum learning is much more sort of involved to get working right than loss weighting. And so you should be kind of cost sensitive here, where you balance like the improvement you get from something against the complexity of implementation, or of like, does it make your method more unstable or more finicky? Just because it makes improvement in performance doesn't mean it's worth having in your model. And so, like Sarah was saying, this could just as well be the outcome. And so what would be the interpretation of this plot about X and Y and what you should include?
So probably just use baseline and X. There's no big improvement to add Y.
Yeah, adding Y does absolutely nothing after you have X. And so you should basically not include it unless you have some other reason that it's not related to performance.
Would it be actively detrimental then to add Y? Like, would you not be taken seriously if you did this kind of work and we're like, we're just going to use X and Y anyway because, I don't know, like, is that bad practice?
It is, and it's usually just because we want the simplest solution that does the job.
Sure.
So if you know something isn't helping, so you could have another reason, like maybe you include it because it makes your model better calibrated or more stable.
Sure.
It doesn't improve performance, and that's fine. You have that's evidence that it's doing something worthwhile.
Mm-hmm.
But if you really know that there's no benefit to it, then you can have a simpler solution, and you can prefer that.
Yeah, the complexity really can grow here because it could be like maybe like in the first plot where like, yeah, you got benefit from adding Y, but also then it massively slows down training.
Right.
Then like there's this trade-off between like the amount you have to pay every time you want to train a model, and or like how big the model is, and then how complicated it is to run inference in the future. So yeah, it's there's a lot of ways to measure the sort of performance metrics of the different things. And there are some computer vision papers where explicitly you'll have things like, here's the benefit to accuracy of each thing, and here's like the increase in the number of model parameters,
Sure.
or the increase in the clock time for inference. And so like you get both dimensions, and you can see that trade-off, and then you can kind of try to pick what's right for you.
So we're going to look at one or two quick examples of real ablations in real papers, just so you can see what these tend to look like. And so one example is augmentations. You've all learned about them. And there are a lot of them, right? There's a lot of different ways to augment your data, and you could do them in any order, right? So there's a lot of choices here about what, how you build your augmentation strategy. And so this is from a paper that introduces a method called SimCLR, and so they have some really nice ablations on augmentations. And so what they do is they make this big old table Where on the y-axis, this is like what you do is the first augmentation, and on the x-axis is what you do is the second augmentation. And they do every combination. So this is obscenely expensive to do, and you'll never do this, but that's the nice thing about industry papers is that they can do crazy stuff like this, and it's interesting.
All they're doing is burning carbon, you know?
And so on the diagonal here, things that are crop and cut out, those are just using one augmentation. So it's, so the diagonal here is kind of like the baseline, and off diagonal is showing other performances when you do one first and then the other, or the other first and then the one, all the different combinations. And so this is about as thorough as you can get with an ablation study. And even here, they didn't go as far as they could, right? Because typically you do 3 or 4 or 5 augmentations, but it would just be insane to try to look at all of the combinations of those. So even Google doesn't check all of their, potential combinations of things.
Why would doing one before the other matter? For like a lot of these, and like they first crop it and then rotate it, like what?
So sometimes it should and sometimes it shouldn't. So for instance, the Sobel one here is a derivative operation. So if you add noise first and do Sobel second, you're taking the derivative of a bunch of noise, where if you take the derivative first and add Sobel second, you're putting the top of the derivative. So they're not all interchangeable that way. That's a good question. Okay, and here's another ablation example from the same paper. I know it's a lot of bars, but every cluster of bars here is a duration of training, right? So on the x-axis, it's like a number of training epochs. And within a cluster of bars, each bar is a different batch size. And so for their method, batch size mattered a lot. For your methods, it mostly won't. But this is another example of a pretty thorough ablation study about the relationship between how long you train and how big your batch size is.
And also something that really wouldn't be feasible outside of industry because nobody else can train with batch sizes of 8,000.
Oh my
Jeez.
You can barely train with the batch size of 8.
So yeah, you shouldn't even want to do anything this thorough, but this is just to get a sense for like when you're reading papers, what do these things tend to look like? And usually there's 1 or 2 axes of variation, and then they sweep a bunch of combinations of things and people will read those ones. And so, thought experiment, imagine that your idea for improving on your baseline worked. If you wanted to do an ablation study, there are 2 steps. The first is that you need to break it up into components that can be independently removed. And so the first question is like, how would your idea be broken up into components? And the second question is, what would the ablation study then look like if you wanted to analyze the contribution of each of those components? Anyone want to volunteer those? How about you, Anton?
Okay. That I think that I want to split in different data augmentation. Also, I want to try with different pretaining weights because I have 2 or 3 possibilities, and also I can just apply the pretaining model and also give that take this weight and training in that with my data, and also I think that I have a lot of pre-processing that I need to manage because for me it's really different to have 3 re-IDs different per batch that only 2 and 3 copies of the same images on only 1. So I think that my pre-processing is really very important.
Cool. No shortage of things to ablate there. That's probably too many, but it's good. It's good. And so usually with this kind of stuff, you really have to pick your battles because you're going to find there's a lot of things you could check. And so often what winds up happening is that the things that are pretty standard get left alone, and the things that are kind of unusual get ablated. And so commonly, this would be terms and loss functions. So I mentioned that a lot because it's probably the most common thing. We say, okay, I'm going to start with some basic loss, and I'm going to add a term that makes it behave in a way that I like, that makes it pay more attention to rare classes, or that improves calibration or something like that. That's commonly ablated. Pre-processing steps are pretty common, especially if they're more expensive ones. So many of them are pretty cheap and pretty standard. So like cropping and flipping during training is like pretty standard and not commonly ablated. But there's some of these methods that will like do fancy things to your images that are based on another neural network, and so that is something that you would ablate. Training data sources and quantities. This is like what Anton mentioned, where I have pre-training here as well, yeah. Well, like you could pre-train on ImageNet, or you could pre-train on data in your domain, or you could do some combination, one then the other. So that's the kind of thing that's often ablated. If you have like clean training data and then also noisy training data, like whether you include both or just the clean set, things like that are commonly ablated. Training duration is another big one. If you train for 1,000 epochs, is that necessary, or did you get where you were going in 100 epochs and then the rest of it was kind of wasted time?
This one comes for free if you keep checkpoints, right? Because then you just need to run your eval with all the checkpoints that were saved over time. So this is another good reason to save checkpoints, is it gives you the ability to understand how your performance changes with training duration without needing to train multiple models.
Do you just mean like saving every X epochs or whatever?
Saving the weights, and then you can point to those weights and generate the results from those weights, and then look at the difference over time.
Okay, we've got one last little topic because it's been kind of underneath the surface for this whole lecture, which we should now talk about, which is that performance comparison often involves randomness. So, as you may have noticed as you train stuff, if you run your method 3 times, you'll probably get slightly different results each time. And so if method B looks like this, it's not a problem, right? Because method A is better than method B every time you try it. They're not really close to performance. So we would call this stable evaluation, where there's a stable ordering over the rank of how well different methods do. But just as easily and often, you get something like this, where the best method actually changes depending on the run. So this is unstable evaluation. And so in everything we've talked about so far, we've been assuming that you can just get to a number that you trust and is a reliable estimate of how well that model performs. But sometimes you need to do some steps before to make sure you can get to a reliable estimate of performance. Do people know where this randomness comes from? Like in neural networks, for instance, when you train CNNs, like why does it change from run to run?
The initial randomization of the weights.
Yeah, the weights are initially chosen at the beginning. And so if we start from scratch, that's true.
And then the randomization of like the input data for each batch.
Yeah, exactly. So sample the training data randomly, and so you're going in a different order through the kind of optimization process. And so, what do we do about this? The simplest one, and the one that is done most often, is to run your model multiple times and get the mean and standard deviation of your valor test performance. And you compare the means then, instead of comparing a particular run to another particular run, you compare the mean performance across a few different runs. This is expensive though, obviously it multiplies your training costs by quite a bit. So another thing that's often useful is to increase the size of your validation set. So depending on the source of your instability, it could be because your validation set is very small. And if it's small, then a small change in where your model winds up can end up having a big effect on the accuracy. In general, evaluation on bigger data sets is more stable. It could also be because your val set is imbalanced, or you're using a not class balance metric. So for instance, if 90% of your val data set is one species and 10% is the other, if your model happens to take a turn where it performs worse on the majority species, then your val performance will tank. and it will be more unstable because sometimes it'll be 90 and sometimes it'll be 10. And so that's not a great look. You want to increase the size of your val set and use class balance metrics if you think this might be a cause of the instability. Training for longer also often helps. So not so long that you overfit. But one common cause of instability is that you stop training before the model has really converged. And so there's just randomness in where you are after, say, 1 epoch versus where you are after 100 epochs. You tend to get like a more consistent behavior after you train longer. And then adding regularization can also help. So if you have a model that is overfitting slightly, then adding some regularization will help it behave in a more stable way.
Regular, that word, you mean, what is that? I think we talk like normalization and regularization, and there's a lot of things that ends in TAION that may or may not be synonyms.
It's a big umbrella term. So it includes things like weight decay. So if you add a parameter to your loss function that relates to how big the parameters in your model are, it's a way to manage the complexity of the model by penalizing having lots of non-zero weights. Or things like augmentation also is a type of regularization. You're basically trying to soak up some of the extra capacity of the model so that it doesn't have as much spare brain power to overfit to stuff.
A lot of the models you guys are using have regularization built in. Like they'll automatically have dropout, for example, which basically says randomly you might just take out some of the weights of the model at any given step to try to like force it to be more robust to like minor changes.
To recap, we were talking about how we demonstrate progress in this area. So if you've done some stuff, how do you show that it's better than something else you could do? I mean, ideally something simpler would be better, but often the case is that you need CNNs to solve some of these problems. And so you need to make a compelling case that you're doing something that is useful and that is not a simpler solution, and that all of the modules in your method are worthwhile and that the complexity you've added is justified. So you use ablation studies to make that case. So we can do questions, and then that's all the content I've got.
Question? I have a question, Eli. Considering that they're all here for a week, what would you recommend they focus on in the context of this type of thing? Like, what would be reasonable to try to do in the next week versus not?
Yeah, I think the two biggest things are kind of assessing the stability of your results. So this can really lead you down dead ends over and over and over again if you don't realize that the ordering of methods is changing from run to run. So I think it's definitely worthwhile to just create your model 3 times and see how different the predictions are. And if there's a really big spread, you should know to be really careful interpreting the results. And if you don't, you can wind up repeatedly like changing your strategy, even though what you're doing is not relevant. It's just that it's inherently unstable. So that's a big one. And I think ablations are a big one for the same reason. It's about making sure you're taking steps in the right direction. So when you try a new thing, just try that one new thing and make sure that it leads to a stable performance increase. And then you can have that be your new thing, and then you can try a new thing on top of that. But don't like add 5 things and then have a complex method where you don't know which parts are important.
I guess you kind of answered my question, but so the repository that I'm working with, OpenSoundscape, it throws loads of augmentations at your data like right off the bat as kind of like a built-in thing. And in the future, if I see something like that, and that they're not easy to turn on and off. In the future, if I see something like that, would that be considered a red flag for a repository where it's just like throw everything at it, see what happens, or is that pretty standard?
It's not that standard. I think most deep learning packages allow you to control your augmentations. What I would expect is that they would maybe have something default as something simple as a default, and then have the ability to control it for like advanced users. But it seems like they don't have that, so I think that's maybe not ideal. But I don't know. They're building this package for a very particular use case of people who don't want to mess with this kind of stuff.
Sure. Okay.
I think it's a design choice on the user interface side.
Great.
It's also, hopefully, you guys are all getting familiar enough with Python that you could add in the ability to control those parameters if needed. And that's not like that's not as big of a challenge, I think, as like changing an architecture. So great.
So hand over here.
Sometimes, for example, I have tried to change the batch size, but suddenly the GPU is not enough memory. So sometimes for add documentation, I need to put the batch size lower. So I need to change, like I am with some documentation, and I'm able to run in 16 batch size, but with other documentation, if I put more documentation, the GPU run away. So I am not, I can't use the 16. So it's better to just go to the batch size that I can check all the experiment, but I know that maybe with 16 batch size is better than with 8. So it's like, how manage that?
Yeah, it's a good question. And so often it is the case that it's hard to change just one thing because there's other constraints on a real system, right? And so you do the best you can. I think in your case, like doing everything with a smaller batch size is one reasonable way. Also with batch size in particular, I don't know about your experience, but my experience is that it's something that doesn't tend to matter a lot if you tune the learning rate for the batch size. So if you fix your batch size and then tune your learning rate, for most methods, some of them really explicitly need a big batch, but for most methods, I think you can do fine by just picking a batch size and tuning your learning rate.
Yeah, I think the difference is just that you might have to train for more epochs with a smaller batch size, and it's not fair to just take one learning rate and then try it with different batch sizes, because there is a direct connection between batch size and learning rate. So yeah, and then tuning learning rates is also something that can be a little, then it's just a lot more runs again.
Yeah, so the learning rate can cover for a lot of things. If
Yeah.
you fix the batch size, you should be able to find a learning rate that works well. But if you then change the batch size, that same learning rate may not work as well.
Yeah. And I was gonna actually say my first ablation, or the first thing I always check is trying 3 different learning rates that are an order of magnitude apart. So basically the first thing I always do is I train the baseline model, and I'll just train that same model, same parameters, same everything, but I use a learning rate of 0.1, 0.01, and 0.001 or something. Or for some reason, a lot of times 0.04 is or 0.004 is a good one. So sometimes I do those, but it is I'll do this order of mags, and that really can have, depending on the method, a pretty significant change.
Yeah, that's so core that I didn't even think of it as an ablation, but
yeah, that is actually
everything I ever run has a loop where it just runs through 3 learning rates on it, or 4 learning rates.
What are the 3 you pick?
I usually do something similar where it's -2, -3, -4.
Yeah.
And 1 times 10 to the -2, -3.
Yeah.
What kind of batch sizes would they before those learning rates?
Oh, with one batch size.
Okay.
And with one architecture, you would try different learning rates to try to get in the ballpark of the right combination of batch size and learning rate.
So typically with batch size, the bigger your batch size is, the bigger your learning rate needs to be. But this doesn't tend to matter until you work with big batch sizes anyway. It's this paper.
What's big?
Hundreds or thousands.
Okay.
It's the paper I was showing you that has an 81, 92 batch size. They have a learning rate scaling rule. Look, every time you increase the batch size by this much, I'm going to increase the learning rate by this much. But I think in most of your cases, you're doing something between 8 and 128, depending on how big your images are. And so for that, I think doing a sweep like this, where you just sweep over 3 or 4 learning rates in order of magnitude, is a great thing to do.
Another really common thing that really can make a big difference is the input image size. Particularly if the things you care about are small. Then of course, if you're downsizing your images and they already were 4 pixels, then now the thing is just gone, so you can't expect to see it. And so that's another really common ablation that's really doesn't really have anything to do with the architecture itself, but it's just it does, because essentially if you have a bigger input size and that first layer of your model, or depending on the architecture, many layers of the model, then have more parameters. So increasing the input size, the input image size, increases the parameterization of your model, which can make training slower, can mean that you can't have a bigger batch size because the images themselves are bigger, and everything won't fit in memory. Anyway, there's a lot of these different comparisons, and I think that places like Google tend to do this thing where they're oh, it's fine, I'm just going to do this massive grid search, and then I'll just pick the one that's the best.
But actually, I'm like annoyed by that in principle because every single one of those runs costs carbon. And I think that people should be instead making intelligent choices about hyperparameter tuning instead of just mindless ones. But then that takes building up intuition, and sometimes it's not that simple. Cool. All right, awesome. Thanks, Eli.